Hello, everyone. I wanted to make a quick video for you. See if I can get this to work with me. Just to work through a couple of the problems that we didn't get to in class. So the first one I want to do is this number 3 in the notes. So it's right underneath where we define inflection points. It's that number 3. So we want to find the inflection points of this function, x to the 5/3. And then we want to use that to find the intervals where f is concave up and concave down. So we know that inflection points are kind of like the critical points, but of the second derivative instead of the first. So we're looking for the place where your second derivative is 0 or does not exist. So let's find our second derivative. So before we find the second one, we have to find the first one. So the derivative of x to the 5/3 is going to be 5/3 times x to the 5/3 minus 1. That's 5/3 minus 3/3, which is 2/3. Okay, so that's my first derivative. And now we have to find the second derivative. And we're going to do the power rule again. We're going to bring the 2/3 down, and it's going to be 5/3 times 2/3. So when you multiply across, it will be 10/9 times x to the 2/3 minus 1 power. 2/3 minus 3/3 is negative 1/3. So there is our second derivative. Now we want to figure out where this is 0 and does not exist. And we're going to lean on our critical point training to figure this out. Because I have negative exponents in here, we're going to do the same thing that we did with our critical points, which is make it a fraction. So that negative exponent is going to bring the x to the 1/3 to the bottom. So I'm going to end up multiplying that 10/9 by 1 over x to the 1/3. And now I can kind of combine those into a single fraction. So it's going to be 10 over 9 times x to the 1/3 power. Okay, so this is my second derivative written as one fraction. And again, just like we did with critical points, we would set the top equal to 0 to figure out where the second derivative was whole thing was equal to 0. And we're going to set the denominator equal to 0 to figure out where the whole second derivative was undefined. Now, if you look at the top, 10 equals 0, that doesn't make any sense because 10 doesn't equal 0, right? There's no variables up top, so it doesn't matter what value the variable takes on. 10's never going to be 0. So I don't actually get any critical points here, or sorry, inflection points, because this is the second derivative. So I'm just going to say 10 does not equal 0, so we don't have to worry about that one. And then for the bottom, if 9 times x to the 1/3 is equal to 0, we have to solve for x. So I'm going to start by dividing both sides by that 9. And then I'm going to get x to the 1/3 is equal to 0. And we have to figure out how to solve this. To get x by itself, we're going to raise both sides to the 3rd power. X to the 1/3 to the 3rd power, you'd multiply those exponents and you just get x to the 1st. And 0 to the 3rd power is just 0. All right, so the only inflection point that we get from here is this x equals 0 from where our second derivative did not exist. Okay, and then to make sure this is in fact an inflection point and to start figuring out where my function is concave up and concave down, we're going to put that inflection point of 0 on a number line, which cuts my number line up into pieces that are only concave up or concave down in each piece. And we're going to test each section here to figure out the concavity. You're going to pick your favorite representative. So something less than 0, I'm going to say -1. And the thing bigger than 0, I'm going to pick 1. And we want to figure out the concavity and whether we're concave up or concave down on each of these sections. So where am I going to plug these x values into? Since I want concavities, you're right, I'm going to plug them into the second derivative. So let's see. My second derivative looks like any of these. You can really pick your favorite. I'm going to pick this one because I think that's going to be the easiest one to work with. So I'm going to have 10 over 9 times -1 to the 1/3. And the 1/3 is just a cube root. So the cube root of -1 is -1. So I'm going to get -10/9 out of this. Okay, so what does that mean? I get a -10/9 out of my second derivative. Because it's negative, that means my OG was concave down, and I'm frowny. Okay, so then now let's check out x equals 1. We're going to plug that into our second derivative, and I'm going to get 10/9 times 1 to the 1/3. Again, a 1/3 power is a cube root. The cube root of 1 is just 1, so this is just 10/9. And since I get a positive value out of my second derivative, that means my OG is positive and happy and smiley and concave up. Okay, so because I switched from concave down to concave up, this is in fact an inflection point. So I can go ahead and box that in and say, yes, x equals 0 is definitely an inflection point. And now I am ready to write out where I'm concave up and concave down. Let's see. So I'm just going to erase the concave up and concave down part here so that I can write my answer in there. I'll write those next to it. Sorry about this. There we go. All right, so the intervals where we are concave up, let's see, we're concave up just on this section here. And so that is everything from 0 on up to infinity. So that is where we are concave up. And we are concave down anywhere over here, which is everything from -infinity up to 0. And again, we don't include those zeros, this 0 here, because that's where my second derivative is equal to 0 or undefined. Here it's undefined there. It's not concave up or concave down. We have an undefined second derivative. So it's not concave up or down there. So we don't include it in either one. Okay, so that was this one, just so you can practice finding inflection points. The other one that I wanted to work was this number 2 after the second derivative test. So again, second derivative test, we're going to use this to classify critical points as a local max or a local min, just like the first derivative test. So first derivative test and the second derivative test actually do the same thing. They classify critical points as maxes or mins, but they do it differently. So the second derivative test uses your critical points. So the first thing that you need to do is find your critical points. And then what you're going to do is plug your critical points into your second derivative, right? So x equals c is your critical point, and you're going to plug it directly into your second derivative. If your second derivative is greater than 0, let's see, second derivative is greater than 0, it's positive, it's happy and smiley, and we are concave up, which means that your critical point there, the critical point that a concave up section has, is down here. It is a local min. And if your second derivative is negative, if it's less than 0, you're negative, you're sad, you're frowny and concave downy. And if you're concave down, then the critical point you have right here is a local max. And if you plug your critical point into your second derivative and what you get out is 0, then this test is inconclusive. It has no idea whether that critical point is a max or a min. And in that case, you're going to be a little bit stuck and you have to go back to use the first derivative test, just like we did in section 4.2. So the first derivative test never fails you, but sometimes the second derivative test can. But the nice thing about the second derivative test is that you don't have to do the number line thing and test a bunch of values. You just have to put your critical points directly into your second derivative. Okay, so let's practice that process on number 2 here. We're going to find our critical points, and then we're going to classify them. So the first thing we need to do is find our critical points. That requires our first derivative. All right, first derivative here is 5x to the fourth minus 20x to the third. That's our first derivative. And again, we're finding critical points. So to find your critical points, you are going to figure out where your first derivative is equal to 0 or does not exist. I'm kind of skipping the DNE part because a polynomial here, this 5x to the fourth minus 20x to the third, will always exist. So I'm going to kind of skip over the DNE part. We just need to figure out where this equals 0. All right, so we're going to solve this, and I'm going to say self. What comes out of everything? And I'm going to say, well, self, 5 and an x to the third comes out of everything here. So I'm going to take that out of everything, and I'm going to get x minus 4. All right, so now I'm going to set each factor equal to 0. So either 5x to the third is 0, or x minus 4 is equal to 0. So x equals 0 and x equals 4 are my critical points. And both of those are in the domain of my OG function because no domain rules apply. So I know I have 2 critical points. Okay, so now we're going to do the second derivative test to classify them as maxes or mins. Cool thing here is you do not need a number line. We are just going to take our 2 critical points and plug them right into our second derivative. Oh, but wait, where's our second derivative? Yeah, we haven't found it yet, so we got to go back and do that. So let's find our second derivative. I've got space down here. So I'm going to do the first derivative of the first derivative, and we're going to get 20x to the third minus 60x squared. There is my second derivative, and now I'm going to take my critical points and plug them directly in here. All right, so when I plug x equals 0 in here, I get 0 minus 0. We get a 0 out. Ooh, well, we'll come back to that because that's confusing and I don't know what to do with that. So now I'm going to plug x equals 4 in. My brain's not going to do this one on its own, so I'm going to go back to my handy dandy TI-30 X2S calculator, and I'm going to have it plug 4 in for me here. And when I do that, I get 320. Again, I just plugged x equals 4 into here and made my calculator do it. And it spit out 320. Okay, so second derivative test says that if your first derivative, if what you get out of your second derivative is positive, then your critical point's a local min. If what you get out of your second derivative is negative, your critical point's a local max. And if what you get out is 0, then the test is inconclusive. So what we've got going on here at x equals 0, that's inconclusive. That means that the second derivative test can't tell whether it's a max or min. And so we're going to have to go back to the first derivative test, and that will tell us for sure if it's a max, a min, or neither a max nor a min. Okay, so we'll come back and we'll do that in a minute. And x equals 4 here, I got 320. That's positive. Because I got a positive number out of my second derivative, my OG is concave up, which means that x equals 4 is a local min. Okay, now if this one just asked you to classify it using the second derivative test, you could stop here and just say, oh, I'm inconclusive here, I can't tell, and at x equals 4, I have a min. But if you were in the real world, you couldn't necessarily stop here. You would have to classify x equals 0. And so you would say, oh, I have to go all the way back to my first derivative test, which requires a number line. I'm going to put my critical point of x equals 0 on a number line, and I have to test things around that critical point. Because again, first derivative test uses slope. To use slopes, we need slopes around the critical point, not at the point itself. So you're going to pick your favorite x values on either side, and you're going to plug them into your first derivative to find the slopes on either side. So first derivative is up here. So I'm going to make my calculator put these in. So I'm going to just store it into A and do 5a to the fourth minus 20a to the third. And when I plug 1 in, I get a slope of 25. Because my slope is positive, I know I'm increasing on this side. And we'll plug positive 1 into my first derivative. And when I made my calculator do that, I got negative 15. Okay, because I got a negative 15 out of my first derivative, that means the slope is negative. I'm decreasing here, and that means at x equals 0, I go from increasing to decreasing, I'm at a max. So second derivative test fails us, but first derivative bails us out, and I know that I have a relative max at x equals 0. And the second derivative test classified a min at x equals 4 for us. So now we've classified both of those as maxes or mins. So that's how the second derivative test works. When it works beautifully. You don't have to plug in as many things, and it generally tends to be quicker. But it can be inconclusive like this one. And in that case, you have to go back to the first derivative test anyway. So sometimes you just have to play with it. Okay, and then the last thing that I want to kind of talk about is graphs. All right, now that we have a second derivative and we're talking about that, I'm going to add the second derivative into our mix of what's going on our functions. All right, so we know that up to this point, if my OG function is increasing, I know that my first derivative is above the x-axis, right? We've talked about that before. I know that if my OG is decreasing, my first derivative is below the x-axis. If my OG has a maximum, I know that my first derivative has an x-intercept there. I know I crossed the x-axis. And if I have a minimum, I also know that I have an x-intercept and I cross the x-axis. Okay. Now we're adding more things to this list. What if I'm concave up or concave down or have inflection points? I want to add that to the mix of this table. All right, so before we get there, let's start talking about how to add our second derivative into the mix of what we have. If my OG is increasing or decreasing, we don't really have enough information to really say much about our second derivative. I can be increasing in concave up. I could be increasing in concave down. I could be increasing in concave up, or sorry, decreasing in concave up or decreasing in concave down. So that's not enough information to say anything about my second derivative. But I do know that if I have a maximum, right? If I'm at a max, I'm going to have to be like this, which means I have to be concave down, which means the value that I get out of my second derivative is going to be negative. My second derivative has to be below the x-axis there. So if I have a maximum on my OG function, I have to have an x-intercept on my first derivative, and my second derivative is going to be below the x-axis there. Similarly, if I'm at a minimum on my OG function, it's going to look like this, which means at this minimum value, my second derivative is going to be positive because I'm concave up and I'm smiley and I'm feeling positive. And that means that my second derivative, the y value, will be positive, which means my second derivative is going to be above the x-axis there. Okay. And similarly, just like because the second derivative is the derivative of the first derivative, the connections between these two are going to mirror the connections between these two. So notice how, because when my derivative was above the x-axis, my OG was increasing. If my second derivative is above the x-axis, if it's positive, I know that my f prime, my slopes, are going to be increasing. So not only am I going to be at an x-intercept, but if I'm increasing at the x-intercept, I know that my OG had a minimum there. And similar, if my derivative is below the x-axis, my OG was decreasing. My second derivative is, if it's below the x-axis, then the OG before that, my f prime, is going to be decreasing. Because again, if we're concave down, my slopes decrease from left to right. So if you have an x-intercept and you're decreasing, your OG has a maximum there. Sorry, this got kind of weird, so I'm going to fix that. My OCD doesn't like that very much. Okay, cool. Now, what if I start adding more things? What if I'm concave up? Well, we just talked about that. These kind of mirror what we just did. If I'm concave up like I was here, I know that this one's going to be above the x-axis. And I know that that means that this is going to be increasing because my slopes increase from left to right if I'm concave up. And if I'm concave down like I was up here, I know that my second derivative is going to be negative and below the x-axis. And I know that my slopes, f prime, is going to be decreasing. So again, these guys are kind of the same. It just depends on if you're at a maximum or a minimum, you're also going to have an x-intercept there. And so there's special cases of where you're concave up and concave down, but the rest will still connect. And then if I'm at an inflection point, that means that my second derivative is 0 or did not exist. We're going to focus on the existing solutions because if it didn't exist, it wouldn't show up on the graph anyway. So we're going to focus on the existing ones. So if my inflection point is there and my second derivative exists, it's going to be 0, which means I'm going to have an x-intercept because my y value for my second derivative is going to be 0. So I'm going to have an x-intercept on my second derivative. And again, just like here, when I had an x-intercept on my derivative, I had a max or a min on my OG. And so that means if I have an x-intercept on my second derivative, I'm going to have a max or a min on my first derivative. Okay, so we now have a more full table here. And now let's practice this with this graph. Now, the hard thing is that sometimes you're going to be given a graph that's your OG function, and sometimes you're going to be given a graph that is your f prime function. And how you answer questions about it depends on what function you're given. So we're going to run through this twice. The first one is if the graph given is f of x, my OG function. So right now, this is going to be y equals f of x, my OG function. Okay, so if this is my OG function, we need to identify where my OG function is increasing, decreasing, concave up, and concave down. Okay, so let's do increasing, decreasing, concave up, and concave down. Okay, so if this is f of x, I can just kind of look at it. Where is this function increasing from left to right? Yep, it's increasing. And let's put solid, let's pretend that this has solid dots at the ends. I'm just gonna fix this. So this has a solid dot here. Let's just say it ends. I don't have arrows. I've got solid dots. Okay. So then where is this function increasing? Well, it's increasing from 0 here all the way up to here, which is B. And then I'm also increasing from here up to here, which is from E to G. So that's where this OG function is increasing. That's I can just look at it and tell. Decreasing is going to be the opposite of that, right? It's from here to here. That's where we're decreasing. It goes from B to E. Okay. How about concave up and concave down? And again, concave up is any part of a smile, and concave down is any part of a frown. So I'm just going to kind of start with what we know. And so I'm going to say, okay, this is frowny, right? That's definitely frowny. And that's the only frowny part I see. And I'm also going to do another one. Let's switch to green where I'm smiley. And so now I'm smiley in here. So my inflection point is going to be where the smiley and the frowny meet, which is right in here. So C is my inflection point, right? And so that means where am I concave up? I'm smiley on the green parts. So I'm going everywhere from C to G. And I'm concave down anywhere I'm frowny, which is the red parts, which go from 0 up to C, because that inflection point cuts this up into pieces, right? That C was my inflection point. Okay, so we can just kind of look at this if this given graph was f of x. Okay, now let's rework this and do it again. But this time, I want to redo all of this, and I want the graph given is f prime of x. Let's pretend that the graph that I'm given is now f prime. That was supposed to be a prime, but it got real wonky. Let's try it again. F prime. There we go. This is now my derivative graph, and I want to know where my OGF is increasing. I want to know where my OGF is decreasing. I want to know where my OGF is concave up, and I want to know where my OGF is concave down. But this time it's harder to just look at it and know the answer, because I'm asked where f is increasing, but I'm given the graph of f prime. So I have to answer questions about a graph that I can't see using this graph that I can. And we're going to have to use the connections between my derivative and my OG. Okay, so I want to know where my OG function f is increasing. Okay, I can't look at the graph and see where I'm increasing. That's not what I'm looking for. I have to figure out what f prime is doing when f is increasing. So I'm going to look at my table. When my OGF is increasing, I know that my f prime graph, which is what we have, is going to be above the x-axis. So I'm really looking for where f prime is above the x-axis, right? Because wherever f is increasing, f prime is above the x-axis. So now I can come up here and say, okay, well, where is this graph above the x-axis? I'm going to switch colors again. Okay. Okay, where is this thing above the x-axis? Well, it's above the x-axis, right here and right here. So those are the places where my OG is increasing. So that's going to go from A to D. And again, I'm not including my endpoints because I'm not above the x-axis there. I'm on the x-axis there. And then I'm going to union that with f to g. Oh, and actually, I want to include g, right? Because I am above the x-axis there. Yeah, I want to include this one because g is above the x-axis, so I want to include that one, but f is not above the x-axis, it's on, so I don't want to include that one. Okay, so that is where my OG is increasing. Okay, so now let's do the decreasing. How would I find where my OG function on a graph I can't see is decreasing? Well, the graph that I can see is f prime. So I'm going to have to go back and say, okay, well, if my OG is decreasing, what's f prime doing? Yeah, it's got to be below the x-axis. So where my OG is decreasing, f prime has to be below the x-axis. So I'm really looking for where this graph is below the x-axis. So where is this one below the x-axis? Yep, I'm below here and I'm below here. So then I can write these intervals. I'm going to go from 0 to A. I don't want to include A because I'm on the x-axis there. I'm not below, but I do want to include 0 because I am below the x-axis there. So I want to include that one. And I'm going to union this with the stuff between D and F. So I'm going to go from D to F, and I'm not going to include either of those because those endpoints are on the x-axis, not below the x-axis. Okay, first hurdle down. Now we have to do concave up and concave down. And again, I'm asking about whether my OG is concave up and concave down, but my graph is f prime. Okay, so let's focus on where my OG is concave up. Okay, I can't see my OG, so I have to rely on the table and connect it to what I can see. So if my OG is concave up, that means the one I can see, f prime, has to be increasing. So where my OG is concave up, I'm looking for where my derivative is increasing. Okay, so I'm going to come back up here and I'm going to say, where is this graph increasing? Well, we did this before. It goes from here to here and from here to here. So that's going to be from 0 to B. And unioning that with E to G. And I'm just not going to include my endpoints because I don't have anything on the other side, so I can't tell whether we're actually increasing or decreasing there. Technically, my two-sided slope wouldn't exist, so we're just going to kind of ignore the endpoints there. All right, and then the last one is if my OG is concave down. Okay, OG is concave down, so the graph that I have, f prime, should be decreasing. So really where my OG is concave down is where f prime is decreasing. So now I can look on the graph that I have and say, where is this thing decreasing? And I'm decreasing here from B to E. And again, I'm not going to include B and E because I'm not actively decreasing there. I have a slope of 0. So I'm just going from B to E. Okay, so just be really careful with graphs in this section. Just like I know the graph problems in 4.2 are giving a lot of you headaches. It's hard to answer questions about a graph that you can't look at. So just rely on these tables. Like I said, I made this table and even this big one on all of my Calc 1 exams. And this thing got me through these because my brain really struggled like hardcore with these when I went through Calc 1. So don't give up. Keep practice writing this table out, get it so that you can write it out over and over and over again, get it on your test, and connect what you're given, right, and what you're asked about to the graph that you can see. That way you know what you're looking for on the graph you're given, even though what you're asked about is on a graph that you're not given, if that makes any sense. So keep fighting through that. I hope this helps. Happy studying, and I will see you next time.